Looking at tracing algorithms, we have two sets of code in Python, one with one recursive call and the other with two recursive calls, and we're going to have a look at two different methods of tracing the algorithm. Here we have a recursive function for factorial, and we're passing in the value of factorial 5. We have a single recursive call, as you can see in the return at the bottom there, and we have set the base case to 0. So creating the trace table for this, first of all we have the level, which is the iteration starting from 0. We then have x, and at the start we're sending in the value of x is 5, and then that will change each time as we do x minus 1. We then have the part of the if statement where if x equals 0, the outcome of that can be true or false. And we then have the return, which we won't be able to work out until we get the factorial of 1. So the first value is level 1, and x will be worth 5 on level 1, that's what we passed in. We then look at the if statement, and does x equal 0? No, it doesn't, so that is false. Now we can't work out the return of the factorial 5 until we've worked out what factorial 4 is. But we do know that x minus 1 is 4, so we can place the 4 there. And then this will take us to level 1. Again, x does not equal 0, so we can put false in there. And then we can work out that x minus 1 is 3, so we can place 3 in the trace table, and this takes us to level 2. Again, the value is false, and we go back and repeat this. 3 minus 1 is 2, and then that takes us to level 3, which is false. Again, repeat. So we still don't know what the factorial is, but we do know that x minus 1 is 1, which takes us to level 4. And then lastly, x minus 1 this time is 0, which means we've hit the base case. That's level 5, and this time it's true. So now we've hit the base case, we know that we're returning 1. So we can now work out the factorial of 1 by 1 times 1, which is 1. And now we know the factorial of 1, we can work out the factorial of 2. So we can do 2 times 1, which equals 2, which then means we can work back up the stack to calculate the factorial of 3. The factorial of 3 is 3 times 2, which is 6. And working up the stack, 4 times 6 is 24. And lastly, 5 times 24 gives us an answer of 120. Now, you could present this table in a view such as this. So when we get to the base case, we continue down the table rather than working back up the stack, simply in reverse, until we get to the same outcome of the factorial of 5 being 120. Okay, now in this example we have a recursive function which has two recursive calls. The first one is Fibonacci of x minus 1 and the second of Fibonacci x minus 2. We're passing in the value of 4, so x is starting with the value of 4, so we can say that x is equal to 4. In this one, we're going to use a binary tree to trace the recursive algorithm, and we'll see how binary trees are great for tracing a recursive algorithm that has two recursive calls. So for start off, if x equals 4, then we don't know what the Fibonacci of this is. So we take the first value, Fibonacci of x minus 1, and we take that to the left, and the second value of Fibonacci x minus 2, and we take that to the right. So on the left of this binary tree we have x equals 3, and on the right of this binary tree we have x equals 2. Eventually we will add these two values together, which will give us the value of 4. Okay, next we go down to the left of the tree and we say the Fibonacci of 3, so that is 3 minus 1, so x minus 1 is 2, and then going to the right, 3 minus 2 is 1. So we're looking what the value of x is at each stage. We still don't know what the actual value to put in this tree is until we get to the base case of x equals 1 or x equals 0. Okay, we fill the same in on the other side, and actually when we can just copy the values of x when we get them from the left hand side of the tree. Okay, so moving down, this time we get to the base case when x equals 2, x minus 1 is 1, and x minus 2 is 0. So we're now at the base case, and the base case says to return 1, so we can return 1 to these values. We then work back up the tree and we can do 1 plus 1, and then that gives us the value of 2 here. Now we know that when x equals 1, the value is 1, so we can fill in the other value of x equals 1. And we also know that when x equals 2, the value is 2, so we can fill that in on the right hand side as well. Okay, so we're now looking at the value of 2 plus 1 on the left here, which equals 3. That then allows us to fill in the other two values of 1 on the right hand side, and then we're left with the last one to work out, which is 3 plus 2 to give us the value of Fibonacci 4, which is 5.